Good morning to everybody. So, today we shall be discussing some elementary concepts regarding the geometric series, and in particular we shall find out in fact the sum of n terms and infinite terms of a GP, and of course we shall be giving some application to solve some problems. Now, all of you know what is a GP. So, if you are given मैडम ये नहीं हो रहा है, excuse me, just a minute. So, these are the main objectives to find out the nth term of a geometric progression, which you have already done, and we will find out the sum of a geometric series, and we will find out the sum to infinity of a geometric series whose common ratio lies between -1 and 1. Now, I will let you know why we restrict this condition on R, that is the absolute value of R that should be less than 1. So, this is just for the sake of completeness. I am simply repeating the things which you have already done in your last lecture. Well, if a progression is of this nature AR is square, AR cube and so on, then its nth term is given by AR raised to power n minus 1, where A is referred as the first term of the GP and R is known as the common ratio. So, these are the symbols which we use very frequently. N stands for number of terms, R for common ratio, A for first term, Tn usually stands for last term, and Sn is sum of n terms. And these are the just formulas. Tn is equal to A r raised to power n minus 1, which you have already done, and this comes out by intuition also, because first term is A, second is AR. You can write AR as A r raised to power 2 minus 1, then AR 3 minus 1 and so on. So, in general Tn is equal to AR raised to power n minus 1, and A is of course Tn upon R raised to power n minus 1. I will derive this formula, that is Sn, which is the sum of n terms of GP. This is A into 1 minus R raised to power n upon 1 minus R. Well, this I won't repeat because you already know this is the formula which I have used just for the sake of completeness. I am interested in finding out the sum of a geometric progression whose first term is A, and there are number of terms in that progression are n, and R is the common ratio. So, this is the formula Sn is equal to A into 1 minus R raised to power n upon 1 minus R, and certainly it is a meaningful expression if denominator is non-vanishing, that is same thing as 1 minus R is different from 0, and that is equivalent to that R is not equal to 1. Now, most of you may be interested how to find out this formula. So, I will derive it. Let us write Sn is equal to A plus AR square plus so on, and AR raised to power n minus 1, where AR minus 1 is the nth term, and we use a very simple trick. What we do in fact is that we multiply this expression Sn by R, and namely we get R into Sn is equal to, and we switch over term A multiplied by r is AR, then AR square, AR cube and so on, and the last term will turn out to be AR raised to power n. And what we do now, we are having these two expressions. So, we write Sn minus r Sn is equal to, well, first term is there, that is AR will get cancelled, AR square will get cancelled, and you will be left with only last term, that is AR raised to power n. Once again I repeat, Sn stands for the sum of a GP whose first term is A, common ratio is R, and last term, which is nth term, that is AR raised to power n minus 1. To find out the sum, we use a very elementary trick, namely we multiply the expression by R, and just after subtracting elementary subtraction, Sn minus r times Sn is A minus A r raised to power n, and this I can write 1 minus r into Sn is equal to A 1 minus r raised to power n, and simply I divide it by 1 minus r, because r I have not taken to be 1. So, this gives you Sn is equal to A into 1 minus r raised to power n upon 1 minus r, and it is our understanding that r is not equal to 1. Now, let us see the very trivial example. You are given this GP 2 plus 6 plus 18 plus 54 and so on, and I am taking the trivial case in the sense there are only 6 terms. So, if you compare this with your original, let us say GP AR square, then in this case we have A is equal to 2, R is equal to 3, which you have got by dividing 6 by 2 or 18 by 6 or 54 by 18, they are the same thing, and the number of terms in this case, that is n, which is equal to 6. So, apply your formula Sn is equal to A into 1 minus r raised to power n upon 1 minus r, put the value of A and r. So, that you get 2 into 1 minus 3 raised to power 6 upon 1 minus 3, and that ultimately turns out to be 728. And of course, before finding out the sum up to infinity, let me give you one more example to find out the sum up to n terms, and that is a bit tricky example. So, I switch over. Let us find out the sum okay, 7 plus 77 plus 777 plus 7777 plus so on up to n terms, meaning thereby is that in the last term there will be n sevens. Now, there is a very simple trick to find out the sum of this type of a series, and that ultimately turns out to be a very simple application of the formula which we have derived for a GP. What I do, I write it as, I take 7 as common, then I write it is 1 plus 1 1 1 1 1 plus so on, and they are n terms. Now, 7 I can write as 10 minus 1, or better you write it as, this is more convenient, 7 by 9, then 9 plus 99 plus 999 plus so on. Now, this 99999 and so on, these are interesting numbers in the sense that you can always write them 10 minus 1 plus 10 square minus 1 plus 10 cube minus 1 and so on. These are total n terms. Now, if you look, you take this term, this term, this term and so on, that is 10, 10 square, 10 cube, 10 raised to power 4, 10 raised to power 5 and so on. This you write it separately and it is forming a GP. So, this you can write as 7 by 9, 10 plus 10 square, 10 cube and so on. This is my one, let us say, part, and rest I can write as 1 plus 1 plus 1 plus 1 and so on. In each of the bracket, I mean small bracket, there are n terms. Now, you see whether it is 7 or 8 or 5 or 6 or any, let us say, sequence of this nature, that can be used, that can be sum out in the sense that is simply divide it by 9 and take that factor as common, and this, the thing which you are getting in bracket, this will be common in all the cases. So, this technique you can apply for these type of series. Now, 10 plus 10 square plus 10 cube and so on, there are n terms. So, this is a GP, and this 1 plus 1 plus 1. So, that is a simple sum, that is minus n. So, this is GP, one plus 1 is 2, 1 plus 1 plus is 3. So, 1 plus 1 plus 1, so on up to n times, that is your n. Now, the sum of this GP is, you use formula, that is A, my formula was A into 1 minus r raised to power n upon 1 minus r. So, in this case my A is 10, r is also 10, now you simplify it and you will get the answer after just simple, let us say, calculation. So, I repeat the process, that if you are having sort of this repetition type of terms, I took just 7, you could have taken 6 or 5 or anything. So, main idea is to find out this 1, 1, 1, 1 and so on, and this 9 plus 99 plus 999 and so on, and rest is a trivial consequence of the formula of the sum of which I have written over here, that is A into 1 minus r raised to power n upon 1 minus r. Now, before I go further, just for the completeness, I recall that if A and B are two numbers, then their arithmetic mean, this is the thing which you have already done, that is your A plus B by 2, your geometric mean, that was your square root AB, and there is one more which is not a part of this topic, but just for completeness I write, that is 2AB upon A plus B. This is called the harmonic mean. Harmonic mean, well, we say a series A1, A2, A3 and so on, that is a harmonic series or harmonic progression. If the reciprocal of that, that is 1 upon A1, 1 upon A2, 1 upon A3, 1 upon AN and so on, that is an AP. So, why I am taking this thing, this is just as a remark you can write that if you multiply AM into HM, this is equal to A plus B by 2 into 2AB upon A plus B, and this is merely AB, which you can write root AB square, which you can write GM square. So, what does it give to you? That is, these numbers AM, GM, HM, they themselves form a GP, because you recall that three numbers ABC, they are in GP if B square is equal to AC. So, this was just for the sake of completeness. Now, I will switch over to the find out the sum of a GP up to infinite terms. Now, let us say discuss a very trivial and very interesting, let us say, problem with you. Suppose you are having a sort of a square and you are having these blocks, and they are, this is a well known story also, 64, let us say, blocks. Why 64? Because in a chess you have these 64 blocks. Now, suppose a student from your class, he is a topper or she is a topper, and your father becomes very happy. Your father asks, okay, have some prize for me. Then you simply say, okay papa, in first block you just give me 2 rupees, in second block double of that, in third block you take the double of that, and so on. Next will be 16 and so on. So, this is one approach through the chess, that is, you are getting 2, 4, 8, 16 and so on, just 64, let us say, boxes or 64 terms. On the other hand, suppose your papa offers you, okay, you take 1 rupees first day, half on second day, and half of half on third and so on. So, not only for 64 days, you take your whole life. You are doing this business throughout your whole life. Then what will happen? In this case, the amount which is coming out to be, that is 2 plus 4, or you can write it in that form, that is 2 plus 2 square plus 2 cube and so on up to 64 terms only. So, the first day 2 rupees, then double, and of course, you go on just for 64 days. On the other hand, you start from 1 and take half of that, then once again half of that, and so on, and you take it throughout the life, means up to infinity. Then, well, these two things leads you, were it too important, let us say, concepts of mathematics. Well, this type of sum up to infinity, if you take, that series is known to be divergent. Well, this is not a part in your, let us say, this lecture, and this type of thing will turn out to be a convergent sequence. And you will surprise, well, this will be a very, very, very huge amount. On the other hand, if you do this business, that is, you take 1, half, half square and so on, this will simply turn out to be, the sum will turn out to be just 2 rupees, nothing. So, why I am taking these examples? Just to make you the concept of what you call, how to find out the sum of a GP up to infinite terms. So, first of all, if you watch out these two, let us say, sequences, then here the common ratio was 2, while in this case the common ratio is half. So, intuitively it looks like that to find out the sum up to infinity, we must have at common ratio to be less than 1, and in fact your common ratio is always taken to be less than 1 to find out the sum up to infinite, and that's, you recall that my sum up to Sn, that was a into 1 minus r raised to power n upon 1 minus r. Now, this sum is certainly depending upon n, and if n is very, very large, as r is given to be less than 1, r raised to power n is very, very small. That is, mathematically we write it as n is approaching to infinity, r raised to power n is approaching to 0. This is the way of writing. And in this case, your sum up to infinity is a upon 1 minus r. That is, if a is the first term of a GP, r is the common ratio, then sum up to infinite terms is a very simple expression, that is a upon 1 minus r. But the condition is that the value of r should be between minus 1 and 1. Otherwise, this sum will not exist. So, in this case, if you apply this formula, then here a is equal to 1, r is equal to half, that is S infinity is equal to 1 upon 1 minus half, that is 1 upon half is equal to. So, if you start finding out the sum of, let us say, GPs of this nature, then that turns out to be S infinity upon A upon 1 minus R. So, let me switch over to some problems. Let us write down this expression. Sometime you are given an expression of this nature 2 point, let us say 317 bar. So, what does it mean first of all? This is equal to 2.317, 17, 17, 17 and so on. So, you write it as a ratio of integers. Okay, this is also simple expression of the sum up to infinity of a GP. This I can write as (2.3) plus ten cube plus 5 plus so on. Now, you look this part, this is once again a GP. So, you can find out the sum of this particular sequence, and of course, you just add 2.3. So, this is equal to 2.3, let us say plus A is your this thing divided by square, this is my common ratio, and this is your 23 by 10, and if you have this calculation, this will turn out to be 17 upon 990. You can do it yourself, and this is ultimately 1147 upon 495. So, this infinite expression as a ratio of two integers by using the simple techniques of the formula, namely S infinity is equal to A upon 1 minus R, can be expressed as 1147 upon 495. Now, again I recall this as the known formula. I give you a simpler proof also. If you do not know the concept of limit, that is the limiting case when n is very large r raised to power n is very, very small, you simply draw a square, and